Okay, let's start. So, a couple of things. Firstly, uh, on the PT, I assigned the PT numbers. I sent an email out. If you didn't get it, that's basically because you didn't fill out the form. Let me know so that I can give you a PT. Second thing is that after scrounging through my lab and all, we managed to find an alternative embed platform, which is what we are going to use. So we have sufficient number of them. I think 25 or so, right, Leon? Yeah. So I think we can accommodate everyone, but just to ensure that you return it, it will be against a deposit. Okay. Of course, you are free to buy your own if you so wish. It's a different platform, same operating system, but from a company called STM, and it's not wearable. It's kind of a desktop kind of thing, but on the other hand, it has a whole bunch of other features. Um, uh, so other than any projects that might need a wearable, I think we should be good to go. So you do need to get the Raspberry Pi Zero wireless or something equivalent. Okay, so today's lecture, so basically this lecture and kind of the following set of slides, uh, I basically want to examine kind of a platform both from a hardware and software perspective. So what kind of things, what kind of issues arise in these embedded devices, and also how the software gets organized. So kind of that's the agenda for today and kind of next week as well. So if we look at a generic standalone device in these systems, um, as we kind of discussed last time, they interact with the physical world. So sensors and actuators are obviously part of it, but that interaction has to be managed somehow. So there's some sort of computing system, which can take a variety of different forms. We normally think of them as basically some CPU, but there are specialized processors like DSPs and such. There are also things which are closer to hardware in terms of how they implement algorithms. So FPGAs and ASICs fall into that category. Then, of course, you would need memory. Sometimes the memory is on chip, so SRAM, DRAM, flash, kind of the usual type of memories that you encounter. Very rare to have disks or magnetic medium on these platforms. I mean, not entirely unheard of. Um, yeah, obviously, in bigger systems you might have them, but for smaller devices, flash is what gets used. Uh, then communication interface. So as we talked about last time, wireless plays a much bigger role in this. And again, when we look at kind of the smaller end of things, then Bluetooth is something that we normally uh, see in our products quite a bit, but there are other radio standards which have emerged in this embedded space. Of course, Wi-Fi gets used, and cellular, particularly for 5G, you would see often they highlight its use for IoT. So currently, devices kind of go through some sort of gateway, but we are headed towards one where your standalone devices, embedded devices, could directly sort of connect to the internet. You already see that in kind of wearables like the watches, for example. Some of them have cellular radios now. But even beyond these, there are other specialized networking technologies that get used. Um, Anyone heard of any, let's say on the wireless side, which are things which are in the products, which you see in products which are more embedded in flavor, or wired technologies for that matter? Any of the home automation stuff that you may have seen, like what kind of, anyone got those smart light bulbs that are quite okay. So uh, there are, if you go through the home automation aisle of Home Depot or on Amazon and all, you would see a bunch of networking standards being used by these products. So one which gets very widely used is something called Z-Wave, which is wireless networking protocol designed for like those smart light switches and stuff like that. Okay, so you can buy like modules and they could be built into the switches and all. It's basically what is called as a mesh networking technology. So the idea is, instead of each device talking to some sort of a gateway, devices can talk among each other, and then one of those devices has to talk to the gateway, so you can kind of do multiple hops. A very similar one is something called Zigbee, and the underlying technology has a mouthful called IEEE 802.15.4, which is kind of the lower layer stack. But this is something that you will find in smart light bulbs and smart meters and smart fridges and smart washing machines and all. A lot of them use Zigbee on that side. Then there are products which use wired technologies which are specialized for this domain. So for example, power line communication. So since devices that plug into the power line infrastructure, they can basically use the electrical wires to communicate. So there was in building automation, home automation, for decades there is something called X10 technology which has been around, and it's very low rate, but a lot of like swimming pool automation and smart blinds and all, they were using that, and there have been kind of advances of that. So very common to use electrical wiring also for this. In the electrical grid, oftentimes the communication between the devices at the building and the utility may take place over the electrical grid. So wired networks obviously are there as well. And then Wi-Fi obviously and Ethernet, these kind of standard networking technologies get used quite a bit. Then for specific domains like cars and aircrafts and all, there are other networking technologies that exist, oftentimes providing some very some support for tight timing constraints and things like that. So for example, there are variants of Ethernet designed for systems which have to meet tight timing constraints. On the car side, there's something called CAN, Control Area Network, which is used quite heavily, and the industry is in the process of transition to gigabit type network interfaces. Not all cars use these, like Teslas, for example, use Ethernet. So we see kind of these domain specific things as well. So rich stuff on the networking side, and likewise I/O interfaces. So by I/O interfaces, I basically mean how peripherals such as sensors and actuators might get connected. So serial connections of different type have dominate this, and then there are obviously things like USB and other variants of this, which various variants of USB and precursors that have been around. And then finally, the human interface. That's the final piece. Sorry, actually, right. So human interface, and then the power subsystem. These devices fall into kind of roughly three categories from the power system perspective. Those that are plugged in, those that operate off a battery, and finally those that operate by scavenging energy from the environment. Okay, so from a solar panel or RF energy harvesting or from motion. So there are all sorts of examples set about. So much of this lecture I want to spend on some of the issues on the computation side, and only lightly touch upon other things, and then as we go along in the course, we'll examine other aspects as well. So when it comes to implementing computation, which is really kind of the place where all the movement of the data and processing of the data gets managed, They are basically historically bunch of different approaches that have existed, catering to different uh, types of embedded systems. So one approach is that you basically create a custom hardware, application specific ICs, or take your design and put it into an FPGA. Anyone not know what an FPGA is? And then nowadays, very common method in the space is that there are companies that sell what are called as IP cores, intellectual property cores, but these are basically designs that you can just put down on your chip and then get the chip fabricated. So like you want to design something which needs a particular type of sensor, a particular communication interface, particular type of processing. You kind of just assemble these and then send out your chip. And it's on this front. Last time I was mentioning RISC-V processor from Berkeley. That's an example of a core, because essentially when it came to these kind of chips, historically the process, if you needed a processor, then that was the most complicated part. And good well-designed processors were very, but basically non-existent. I mean, they were simple 8-bit micro type stuff, but when it came to 32-bit things, there were relatively few good designs. So ARM dominated that. Question? No, so actually Intel is not in that business, but for example, ARM is. Okay, so ARM is a British company which designs processors, and then they basically sell you the design, and then as a vendor, you basically will make your own silicon using that design. There are a bunch of other companies also. Yeah. Okay. So think of it like source code for hardware. Okay, so hardware nowadays is chips and all are not designed by laying out transistors and all. You basically write code in what are called as hardware description languages. If you have taken 216, anyone taken 216? Yeah, okay. So Verilog is what's used out there, right? There's another language called VHDL, and then there are a bunch of other languages which are even higher level, like System C and things like that. But the idea is that the design of hardware nowadays, the starting point is pretty much the way you think of software. You write a piece of code and then you go through a compilation process. It's just that the output of compilation, instead of being assembly code or object file or executable, is the layout of your chip or the layout of the FPGA. So when we say about IP cores, they're kind of, so these vendors tend to be in one of three business models. One is they will basically sell you the compiled hardware design. Okay, so they've already gone through, it's ready to place. So it's like basically some shaped thing which you put down on a particular silicon technology on your chip. You don't get to know what the starting point was. Okay, and of course they make you sign all sort of legal instruments that you will not do the equivalent of disassembly, so you will not do reverse engineering and all. So that's one. Second one is that you pay more money and you get access to the HDL level, the source code. And then the final one is, and which very few companies are able to afford, is that you become an architecture licensee. That is, you get the rights to modify things and design your own processor with the same instruction set. So for example, when you look at ARM, there are only 3 companies which, as far as I know, have the architecture license, so they can design their own processors with compliant with ARM: Apple, Samsung, and Qualcomm. And even the latter two have moved away from it, so they basically use processors that ARM designs, and then they just put them on the chip. Apple, of course, makes its own A series processors which run the same instruction set with, of course, Apple enhances. More common model, so like the chip on that Hexaware that I had shown, that uses an ARM chip, but that's just the company behind it, which is NXP, which makes the silicon, and they use one of the processors designed by ARM and they just put it down on the chip. Okay, so that's kind of their model. There are other companies which specialize in other type of cores, like it might be a radio receiver or an Ethernet interface or things like that. There are also open source websites. So there's something called opencourse.org. You go there, and just like when you go to open source software repository, there's an open source hardware repository with Verilog or VHDL or some other similar high level code that they provide. And the equivalent of compiler tools, unfortunately, here tend to be relatively costly. The companies like Synopsys, Cadence, and all, who basically make that toolchain. Often in the past, they are referred to as hardware compilers or silicon compilers, but essentially they look the same. So, and your target could be silicon or could be FPGA. So, pretty routinely done. And since designing good modules is pretty requires a lot of domain knowledge. So, just like if I need a good machine learning implementation, I could either ask my students to do it from scratch, or I could go and buy, or open source. It's the same model in hardware also. Second one is that you say, okay, I'm not going to make my own chip or FPGAs, but I'm going to make my own board, and then use existing chips that may be out there. Many people do that. For example, in my research group, we often work at that level. Then you create, the third level up is you create a custom system, kind of some sort of a box, using off-the-shelf boards. So there are companies which are in the business of making single board computers and boards with specialized peripherals and stuff like that, and you sort of buy, and there are various buses and all using which you can plug them. So a lot of industrial embedded systems are basically done that way. So I'm talking about things in like big ships and aircrafts and factories, and also you buy these chassis, they have multiple slots, and there are companies like National Instruments and all will happily sell you fairly overpriced things. But that's how things work. So there are racks and racks, and you kind of plug stuff in. And then finally, sort of the other extreme is you basically use just a general purpose computer, but perhaps running with some specialized software or even a different operating system. So many embedded systems are basically ruggedized PCs, or maybe a ruggedized smartphone or iPad or things like that. And then you attach interfaces to them to hook things up. So you'll find embedded systems kind of all across the spectrum. Of course, the interesting stuff really happens up there. From the hardware perspective, and from the software side, kind of down below. Now, these choices have impact, have ramifications in terms of kind of system you're targeting. At one level, if I were to sort of look at those choices from a different ways, really about the degree to which you are customizing the hardware and the degree to which you're sharing the hardware. So I tried to draw this analogy that hardware and software is kind of I'm basically expressing an algorithm, and my starting point looks kind of some sort of a programming language. But what happens after that is considerably different. If we were to look at the choices that as a designer one may have, so at one end is microprocessors. So I'm referring to, let's say, an Intel x86 type thing. General purpose, you have a variety of choices. You can buy a server class processor with gazillion cores, or you can buy an Atom with sort of just a couple of cores, different power performance numbers and all. But it's a general purpose device. What you benefit from is that Intel has already done the hard work for you. What the disadvantage is, of course, you really, other than whatever customization you can do in software, you really don't have any ability to optimize. And also, it's designed for a general workload. So maybe your particular application could have benefited from some specific features, but tough luck. Then next up in specialization are the what many people call as domain-specific processors. So the idea out here is still a programmable processor, but one whose architecture has been specialized to a narrower class of applications. And perhaps the most common ones in this category kind of are the first three that I've listed out there: microcontrollers. So microcontrollers are basically processors which are designed to have lots of I/O to interact with sensors and actuators and things outside. I'll have some later slide kind of going into it, but you can think of them as a simple microprocessor with a whole bunch of surrounding peripherals all on a single chip. Graphic processing units, so these used to be the realm of general purpose computers, but because firstly, because image type data plays an important role in a lot of embedded systems, and besides machine learning algorithms which benefit from the similar computation, so there are a whole category of embedded GPUs and all that have emerged. And in fact, a good topic to explore in projects. I mean, there's a lot of interesting work happening there. Digital signal processors, they have been around for a while. Texas Instruments and Analog Devices are a bunch of companies who specialize in this. These are processors which are optimized for signal processing. Now, what does that mean? If you look at the signal processing computation, is there any particular computation that dominates there? Fourier transform, what else? Same thing, FFT, Fourier transform.
I guess you just have to you can have a choice to implement a filter through hardware.
Sure, so what's common in filters, in most filters? Can you think of a more primitive operation there? Think even more primitive. Yeah, convolution, sure. But multiply, accumulate, right? I mean, all those filters and all, deep down somewhere, it's like x plus some constant time, some other variable, right? I mean, so this multiply, accumulate is at the heart of how you implement a large number of signal processing, at least the type. I mean, I'm excluding from this kind of the more non-linear type stuff and all, but almost everything kind of boils down to that. It's matrix multiplication, matrix vector multiplication. You're doing a kind of whole bunch of operations like that. So what you would find in DSPs is they would have ability to operate on vectors, but the key measure that they would go after is could they do multiply, accumulate very rapidly. So you'll find in DSPs a MAC instruction, okay, single cycle multiply, accumulate. Then you would find accelerators or specialized units for doing FFT, indeed, because what happens in FFT? How can you speed up FFT? Anyone remembers? When you access the array on which you are doing the FFT, how do you access it? No. Yeah, but butterfly addressing of the addresses, right? It's not it's not. So when we work with arrays, we just go 1, 2, 3, 4, 5. Okay. In case of FFT, there is kind of a particular access patterns on the address, and so they provide support for it. So I'm just citing these as examples of kind of operations that in these domains get explored. There are also other things like crypto processors. So it turns out in crypto, a lot of arithmetic happens over finite fields, basically in groups, and there are things on what are called as elliptic curve cryptography. Okay, so these are other type of integer arithmetic, and again, the so-called crypto processors provide support for that kind of arithmetic. And I guess the latest in this domain-specific processor to emerge are so-called neural processors, which are really designed to speed up the computation found in neural networks. So these kind of domain-specific things which exist, and basically what they provide to you is, because of the specialization, better performance, or same performance at a lower cost. Then next up is what are called as application-specific instruction processors. So they're kind of in the same mold as domain-specific, but now they give the end user who has sufficient amount of money an ability to customize the processor. So there's a company called Tensilica which made its name around that. But the idea is that you buy their whatever system, so to say, and then you can modify the instruction set. You can say, I don't need these instructions, let me discard it, and by the way, I need this funky instruction, let me add it, and then they'll generate for you a processor core design which does that, and by the way, they'll also generate the necessary compilers and all for you. Okay, so you kind of get the whole package, because it's one thing to create the hardware, but if you don't have the ability to compile to it or run an OS on it, then it's useless. So Tensilica is perhaps the main example in that category, but there are, I'm sure, others that I don't know about. Then next up, reconfigurable system on chips. So system on chips, as the name implies, refers to that I want basically the entire system in its entirety on a single chip, and ideally I should just be able to plug in a power supply and good to go. Now there's no such thing really, but fairly good approximations to it. Reconfigurable refers to that we can modify it, we can program it. So typically these things look like on a single chip you will have a processor, perhaps an ARM core for example, and it will be surrounded by FPGAs. Okay, so sort of programmable wiring and gates. So then you can take your design, you can figure out, yeah, this goes to software, this goes to hardware, partition it, the FPGA handles that part, which goes into hardware, and the rest of the stuff going to software. And how you partition it and all, there are tools which what are called as hardware software co-design tools, which work on it. So the idea is now my starting point is my algorithm, and then the tools take care of dividing it up and mapping the part which is supposed to go into software into the processor, that's supposed to go into hardware into the FPGA, and then later on you change your mind and say, move this thing from software to hardware, rerun the tool, it does that. So for many things, sort of, if you are able to afford those kind of tools and all, these things exist. Then next up, FPGAs, which are basically reconfigurable SoCs but without the processor, so just the FPGA. But then oftentimes you face this thing that, but I still need a processor. So there are so-called soft processors, which are essentially processor cores which you run on the FPGA. So now you have an FPGA on which part of the FPGA is devoted to implement, let's say, a small ARM processor, and rest of the FPGA is used to implement the hardware logic. So those are called soft processors, and so if your FPGA is sufficiently large, then you can run a processor on the FPGA and then obviously run the operating system on top of that processor. So multiple levels of indirection going on. And then finally in the customization end is ASICs. Then now you say, I'm basically going to, I know what I want and I'm going to put everything down in silicon, and then there are various ways to speed up the fabrication of the ASICs also. So that whole spectrum. Now, as you might imagine, when it comes to performance, I should do better at the bottom end, more customization of the hardware. And likewise, when I look at power consumption, again, I should do better out here. So power will go up as I go up, right? I mean, roughly speaking, if I were to distill kind of things that happen, same operation done here is 10x more costly than done on FPGA, and is 10x more costly than done on the ASICs. And the reason is the following. Let's say I want to do 1-bit AND. Well, that would be just an AND gate here, but it would be a whole 32 or 64-bit instruction up there. Okay, so there's a lot of wastage going on. So that's one thing. The other thing is up here, since it's designed for a general purpose workload, there is a lot of hardware which maybe your application will never exercise. They're still sitting there, and then also if you need like bit widths which are different, then again a lot of inefficiencies out there. So generally more wastage and more unused stuff, whereas here you are able to optimize it and kind of in the middle. The other thing between hardware and software is the notion of sharing. So in software, one of the things we are very good at doing is reusing stuff. So the same arithmetic unit in the processor in one instant is being used by one application, and later on a different application comes and starts using it. Whereas when you hardwire things, then if I let's say put an FFT module on my chip, and I'm not doing an FFT, then it's lying idle. So that's the disadvantage of a hardwire design. And so this whole sort of trade-offs can often get subtle in the sense that you may it's not obvious where you should reside. Much depends upon details of your particular applications and all. And finally, cost. So cost is a trickier thing out here. So what do you think? Which one would be cheaper? Okay, would I mean lower cost here or lower cost here?
Like generally like lower cost and higher the top of the chart.
So lower cost up there, right?
Generally.
Okay. So sure. So now let's think about it. Let's say I'm NASA. I'm designing. Let's say I'm designing something, and I'm designing one of that. Okay. So for one of that, I'll go and buy a processor, and whatever these processors may be anywhere from $1 to let's say $1,000, depending upon what type of processor you're looking at. But that's what I'm going to pay. Whereas if I'm out here, I'm designing my own, then I have to pay for all that design effort and masks that go into making chips and all the non-recurring costs and stuff like that. So that first unit is very costly out here because here I'm riding on the large market that exists. But on the other hand, let's say I'm US Army and I'm going to be creating something which every soldier will carry. Now my volumes are much higher, or maybe Apple, and I'm going to design something and 100 million of those things. Now I can afford to be out here because the recurring cost gets amortized. So the economics of this depends a lot on the volume that you are after. And then there are users like the NASA example I was going after, where it's just so important that even if it is one rover going on to planet, I'll make my own design. I mean, it's just the trade-offs come that way. So for the same volume, well, I mean, depends on what, if it's volume of one, or for small volumes, microprocessor would be cheaper. For very high volumes, it would be cheaper out here, right? Let's look at cost numbers, right? I mean, microprocessors, server class processors are probably a few $1,000s. More typical desktop type processors are a few $100s, and microcontroller type, DSP type of stuff are, let's say, order of $10. Okay, FPGAs, stuff out here. High-end FPGAs could be $20,000. Okay, I mean those big Xilinx FPGAs, which can, right? I mean they can be pretty expensive. More modest FPGAs would probably be, say, order of $100 or so. And there are of course really low-end stuff also. Chips, if you were to just literally fabricate from scratch, then in a comparable silicon process, then you are upfront just to get the masks that are used to make the chip, and I'm here ignoring all the other cost and all. The masks alone are millions of dollars. Okay, so just
why for the pieces of application specific ICs we are considering using it from scratch?
Because no one else is interested in your ASIC, right? I mean, you are making something just for your design. Who else will buy it? So you have to bear all the cost. Whereas here the cost is being distributed across all the customers.
So we're talking from the
Yeah, you're talking from a user perspective. Absolutely. So you are, whatever, a startup, you have to make a choice. So this is where VLSI cost model becomes important. Total product cost, non-recurring cost, plus number of parts that you intend to produce times the recurring cost, right? I mean, like that's true for almost any product. Then there are a whole bunch of fixed costs which feed into that NRE part. So there are EDA tools and training kind of things will happen. There would be the design cost. I mean, generally speaking, if you're designing hardware, it's more costly for the same algorithm than to write the corresponding software. You also have to now budget for testing and all. You have to get those masks made, and also just that non-recurring cost for something modestly complicated would be pretty huge. And then the variable cost is the cost of the silicon, the cost of making it, the cost of testing it, and this is where simpler things would have more advantage. So like a simpler ASIC obviously is smaller in silicon, so the silicon cost of that would be lower than whatever Intel's or processor or Xilinx FPGA, but depending upon what P is, the overall cost structure will be very different. So one just has to sort of think about that. So it's a usual break-even type analysis you can do, where what kind of sort of cost per part you will end up with for your particular volume. Now, having said that, I mean, a lot of interesting embedded systems really fall into the actually, let me step back. One other thing also is that your choice is also dictated by just the absolute performance requirements, right? We know that the performance is better at this end. So for some application, it could be that cost aside, I just cannot do it out here. Okay, so of course that's a hard constraint. Yeah, but there are lots of applications where microprocessors and domain-specific processors and all are perfectly fine from performance perspective, but the cost perspective may dictate different things. The other thing is historically, when if you look at things, often may not be possible in the programmable world initially, and later on as the processors become more powerful, you can do it there. And so like if you look at computer vision or speech recognition and things like that, then in 90s and all, there were a lot of efforts at making ASICs for them. Okay, and now you could just run it on a corner of your processor. Okay, on the other hand, again, there's a new class of applications. Like right now, people are making ASICs for machine learning algorithms, for neural networks, and perhaps a few years from now, that will become more easily manageable within the processor. So there is no fixed answer to this. Much depends upon how technology evolves, but the trade-off nevertheless is there. Okay, so generally speaking, very high volumes, the lower end is better. For very low volumes, the higher end, that stack was better. So the cost kind of looks like this. Okay, so additional factor, which this is not a technical thing, but just nevertheless important, which is the other thing which comes into play out here is if you are at the upper end of that choices, then you're only designing the software, and there's very little hardware uncertainty. So presumably you can get to market more rapidly. And on the other hand, if you are undertaking the ASIC design and all also, then not only are you going to write the software which will run inside that ASIC, but you're also taking all the uncertainty and the longer lead time for making the silicon. So this is where the impact of lost sales comes into play, which is now that you are behind in the market, then you may miss the peak demand, and that has cost. So oftentimes what happens in products is that the first release may come out making use of FPGAs or something, even with a loss there, just to capture the market, and meanwhile your ASIC and all is being done, and then you sort of switch over to that. So there's a gradual sort of refinement that takes place there. So so a lot goes in there. There are other things also in this which comes into play. What is your yield? Intel presumably or Xilinx presumably have refined their designs considerably, that they are, for every part they manufacture, with a very high probability it comes out functional, whereas you will have to take all those risks also. What if the hardware you design has a higher failure rate? You also have to I've already talked about on the slide, training cost, and also there are a whole bunch of other issues, and it's a combination of things which sort of come into play. So in embedded systems, at least the bread and butter compute unit is the so-called microcontroller. And a microcontroller, basically often simply referred to as an MCU, is basically a CPU core with ROM and RAM and peripherals. So it's kind of largely designed to be self-contained. So the goal being that an entirety of what we normally think of a computer is sitting there. Okay, now not fully true, but close to it. Majority of the CPUs sold nowadays are in the form of MCUs. So oftentimes there are these cute plots. They show that Intel sells so many x86, but that's like maybe 10% of the market share of CPUs. Most CPUs are sold in the form of MCUs, and as the MCUs have grown in capability, nowadays you find MCUs which have 64-bit processors, and also while they may still not be comparable to the Xeon type processors or the equivalent AMD thing, but they're sort of pretty powerful. So, but like if you go back 10-15 years ago, MCUs typically meant 8-bit processors or 16-bit processors. Chip vendors, I mean, they could certainly develop their own CPU core, but that's very rare because then you are undertaking having to design compilers and everything like that. So much more common is to license them, and which is what we were talking about earlier. So ARM is the dominant player when it comes to licensing of CPU cores, or in the recent 4 or 5 years, the Berkeley RISC-V has emerged. There are other open source cores also. Sun Microsystems, which probably most of you are too young to have heard of it, but it was a major computer company which died in, I think, in 90s. But they had a processor called Spark, and they released an open source Spark, which is available in Verilog VHDL form. You can download and compile and run on an FPGA or make a silicon or whatnot. But at this stage, it's a little bit stale. I mean, not very many people use it. RISC-V is kind of the new kid in town. Everyone loves it. There are a lot of academicians and companies and all who are making their business plans around it. So RISC-V is gaining a lot of attention, to the extent that there's a bit of, I guess, ARM versus RISC-V kind of tension which is developed. And there's a whole bunch of MCUs. If you go to any of the companies which make these MCUs, you'll see that like Intel may sell, I don't know, maybe order of 10 variants of the CPU at any given time of the microprocessors, whereas these companies will probably have a few hundred, because remember, you also have ROM, RAM, and peripherals. So they sell different variants of these MCUs with kind of different amount of RAM, ROM, to accommodate different cost and power budgets and different type of peripherals. So there's a rich menu you will find, and kind of you go and select what do I need and sort of go with that. So when we look at microprocessor versus microcontroller, in some senses a microcontroller is really a microprocessor, which is microprocessor is a CPU core, so control logic, registers, ALUs, this together with these other things, all on a single chip. So major manufacturers in this side, companies like Atmel, Texas Instruments, ST Microelectronics, NXP, and I'm sure I'm in a whole bunch of things. In fact, this is a very American-centric view. In recent times, a lot of companies in China have emerged, which are making some pretty cool products. So rich space. Yeah. Okay. So so what happens with microcontroller is a lot of things which otherwise would be on the board is now on the single chip, but of course nowhere near in the same size. So the amount of memory and all that you would have is very little. In fact, most microcontrollers do not allow you to plug external memory. So if you look at a microprocessor, it would have address data bus, which is going to go out, and you can put memory mapped things, memory and peripherals, onto that bus. Whereas in microcontrollers, all you would have at the boundary of the chip would be general purpose I/O and serial lines and things like that. There is no address data bus. It's too expensive, because moment you have address data bus, then you're talking about lots of pins, huge package, cost becomes too high. So the goal here is take that part which would normally require very large number of I/O pins, put it all on a single die. The challenge they face is that when you are working with microprocessors, when your memory is separate, then your memory could be designed in silicon process which are optimized for memories like DRAMs and all, and your processor could be designed in the silicon process which is optimized for that. Here, the same process has to handle everything. So you would normally not see DRAMs out there. And the reason is that DRAMs are designed using very different processes, which are not the digital processes. There are so-called embedded DRAMs, which do exist, but by and large, you would see SRAM and some sort of read-only memory, usually flash, would get used out here. Whereas when it comes to microprocessors, most systems end up using DRAMs just because they give you much more bang for the buck. Okay, so I mentioned earlier on that there are these programmable system on chip. So now you can think of these programmable system on chip as being MCUs together with the stuff that would have gone on the board, like the sensors and all, and analog circuitry also sitting there. So, usually these kind of chips, an example is the so-called PSOC from a company called Cypress, but there are a few others. So what happens is now what these guys would have is they'll have the MCU, so they'll have basically the CPU core, ROM, RAM, some peripherals, but they would also have some FPGA, and they will also have some programmable analog circuitry. So like this particular one chip, on the analog system, they provide a whole bunch of op-amps and sort of configurable structures, so that a type of things you would need to do to hook up with, let's say, a sensor like amplification and stuff like that, you can just implement out here. Not very high quality, but sufficient that for a lot of applications, all you need to do is take this and just hook up your external sensors, okay, and it takes care of all the stuff out there. So PSOCs are pretty nice devices, sort of in many applications. I think their first big design was the iPods. For their touch interface and all, used to use the PSOCs, but it's used in quite a few products. So that's a spectrum of choices that exist. What distinguishes this from general purpose computer side is the immense diversity that exists out there. So I already referred to that. You go to TI's webpage or STM's webpage, you literally have like a palette of hundreds of devices that sort of exist. In the manufacturer side, ARM, as I've repeatedly mentioned, kind of dominates, but there are other players that exist. Actually, before ARM, the one which used to dominate, and maybe in numbers still does, is Intel 8051. That was an old microcontroller from 70s, and from in the 8-bit world, it ruled, although it was not terribly efficient and all, and so gradually it kind of got taken over. TI, Texas Instruments, made a whole bunch of very interesting products, but in 32-bit type stuff, ARM is what kind of dominates. So just to give you an example of kind of things that some vendors might offer. So this is ST Microelectronics, one of our dominant vendors. You go to their website and you would find that they provide families catering to different use cases. So like for example, it's hard to read out here, but this is ultra low power, this is wireless, this is mainstream, this is high performance. So they basically been by kind of different target markets. So if you are very power constrained, you're really looking for like something which is microwatts and with very low power sleep modes and all, you'll probably look out here. So they provide that level of thing. Then within each one of those families, they will have a whole bunch of other choices. So you see out here that different frequencies, different amount of memory, and sort of different kind of power management. So a whole bunch of choices that they provide. One thing to also notice that memory is extremely power hungry, because moment you have static RAM, then its state needs to be maintained, and that burns power. So selecting MCU which has excessive amount of memory has a persistent cost, not just dollar cost, but power cost also. So choices kind of matter, And just wanted to show that, I mean, just lifted from their website, that even in that ultra low power MCUs, they provide sort of a whole family of choices. So what metrics to consider? So when you're selecting these things, so certainly performance is one, and you would find that the choices nowadays across the full spectrum of MCUs range from kilohertz. So there are really super low power MCUs designed to run at single digit kilohertz. They're supremely low power, to then things which run at, let's say, modest number of gigahertz. Raspberry Pi, for example, Raspberry Pi 3, I think, runs at 1.4 gigahertz. So you kind of get the drift that we have the whole spectrum out there. Power, microwatts, and actually there are even stuff which is at nanowatt level now, all the way to watts. So Linux, things which are capable of running Linux would probably be, let's say, order of 1 to 10 watts. On the other hand, things which are at the microwatt and picowatt are too tiny to run any operating system, and you'll probably be programming in the raw. The type of processors which are running mbed range, let's say, in the milliwatt spectrum. Program memory. So program memory, so in our general purpose computers, the program resides to begin with in the hard drive or flash drive, and then it is brought into the DRAM, and then pieces of it are brought into the cache in the processor. So we have, and the cache may have 2 or 3 levels, right? So this code kind of percolates close to the processor until the processor fetches it. In the MCUs, it's much flatter. Usually instruction caches are not there, or maybe there is one level of caching, and the program resides on the flash memory on chip. So very typically these MCUs are designed so that the processor fetches the instruction from the flash and executes it. So none of that 3-4 level of hierarchy that is common in normal processors. Data memory, in some MCUs, literally it is in bytes. You might find things where it might be just a couple of 100 bytes to megabytes. Remember, it's sitting on chip, so anything more is just out of the question, and even megabytes would probably be a couple of megabytes, nothing huge. Just by way of comparison, modern Intel processors have caches which are tens of megabytes. Okay, so very different world. One of the implications out here is that you have your coding and all has to be really optimized for memory. Okay, that matters a lot. I/O. So general purpose microprocessors basically provide you an address data bus, and then you put stuff on the board to hook up to it. On case of MCUs, the buses are inside the processor chip, and then what you get outside are GPIO, AIO, and serial buses and all. Okay, there is no address data bus which comes outside. Usually they will have a whole bunch of peripherals, and in particular peripherals like timers, counters, A to D converter, D to N converters, network interfaces, radios even, or codecs or FFT units and stuff like that. So a rich milieu of stuff exists on chip, whereas if you are using Intel processor meant for desktop laptops, most of this stuff is outside basically. Oftentimes as part of chips that Intel provides for putting on the PCB, so the system control chips. Internal functions. So for the longest while these were things like DMA. Anyone knows what DMA is? What? Not allocation, access. Okay, what does it do?
That's devices like memory without the CPU.
Yeah, exactly. So basically you can almost think of it as there's a second processor whose task is to move stuff from devices to memory or memory to device without so the main CPU can go sleep or do something else. Okay, so it's very commonly used to either save power or to increase performance. Caches I already referred to. Memory protection. This is a very important part of systems where multiple things can exist. So in case of our normal computers, how is protection, how are regions of memory protected? Like what feature of computers ensures that application 1 doesn't crash application 2, or if both of us are logged on to the same server, I'm not crashing the memory. Like, so a big and fairly complicated part of modern processors is what is called as virtual memory. Okay, so basically what happens is each application gets a view as if it has its own computer. Okay, and address space which runs through the entire possibility. And then behind the scene there is a mapping from this virtual address to the physical address. So it could be a particular part of my virtual address resides in one part of the physical memory, and for a different application or a different user, a part of it resides. So we all share this underlying physical memory, which could be a lot smaller. So if you think about it, in a 64-bit or let's say a 32-bit computer, the address is 2 to the power 32. That's 4 gig of memory. These devices don't have anywhere near that. So we all reuse the thing, and all that magic of going from virtual to physical is handled by the virtual memory thing, and that's a fairly complicated piece of hardware. It has to track a lot of things and kind of work with the operating system. So in systems like my laptop, this is how things are done. But if you look at the complexity of those units, they are so much that they are actually far more than the smaller processors. So not viable. So memory protection in MCUs is usually non-existent. That is, everything is operating in the same physical memory space. There is no virtual memory. So if something goes wrong in program 1, it will crash program 2, and you have to be, so that's a problem. Or in some recent processors, they have begun to provide some modest support which you can then use to do things. So like ARM processors provide something called MPUs, and they are kind of a very simplified form of, it's not virtual memory, but very simplified form where you can say this area of the memory can only be is non-writable now, or things like that. But they can still be bypassed, so they're not a sure shot kind of mechanism, but that's a hit concern. And then finally, secure enclaves. So secure enclaves refer to it's something started in general purpose processors, but is now also emerging in embedded processors. And this refers to the fact that oftentimes now we run applications on third-party devices. So what I mean by that is you may run some computation on a processor on Amazon Cloud, or Google may want to run some piece of code on a device which is at your home. So we are often running applications where the platform is someone else's. And if my application is dealing with sensitive data, then I have to worry that the underlying platform may have been hacked. So just to give you an example, it was very common practice that people would mess with MAC Ethernet addresses and clock on their computer systems in an attempt to cheat the license, the software licensing or the content licensing that would exist. And that was basically you're compromising the platform and the application loses. Okay. More generally, the operating system, if it is compromised or hacked, can steal information and all. So secure enclaves is a new capability that modern processors have, where there is a portion of memory and a way of running inside using that memory where operating system cannot examine that. Okay, so we basically are letting the application trust that even if hardware and OS have been compromised, things will still be okay. And we see this in embedded systems also now. So a lot of ARM processors have something called trust zone. And essentially, what trust zone does is, in these embedded processors, it gives you kind of a normal operating mode and a secure operating mode. And if you switch to the secure operating mode, the normal, anything running in the normal mode has no way of accessing it. Or at least that's the theoretical, that's the guarantee they seek to provide. So lots of things are happening in this side also. And then finally, another thing to consider is what kind of cost and software tools and debug support exists. Embedded systems are have a very different type of software development cycle. On your laptop, you write the code, you run it there. But on embedded systems, you write the code here, you compile it here, and you have to then inject it into the into that device. So how you do it? Does it allow on-the-fly changes, over-the-air changes or not? How do you debug it? There is no screen attached to it, so what happens when you do a printf, and all those kind of things come into play. There are specialized debug devices, stuff like that. So again, that support matters. So oftentimes, like, maybe the processor is $1 cheaper, but if the tools are awful, then you will pay on the software development side. So that trade-off kind of comes into play. So that's the set of metrics to consider. So let's see, it's 5 p.m. or so let's take a 5-minute break, and then we will resume this. So 5 minutes.
For the two modules you introduced, should we buy both of them, or should we still wait?
Pardon me?
Should we still wait for you to tell us which one to
No,
buy,
so
or
you should just buy the Raspberry Pi one.
Yeah.
Yeah, that sounds good.
You have a discussion section?
Office hours, you mean?
Oh,
There's no discussion section.
there is in the course list.
Discussion section in the course list?
Yeah, to every course.
Since there is no official TA, so there is no
Oh, okay.
discussion section.
Okay.
Yeah. Yeah, I didn't know that. I'll find out from the department what do they have in mind, because normally this course never had a discussion section.
Okay.
Okay.
So the discussion session is the office hour?
Have they given a room number and all for discussion section?
I'm not sure. Let me check quickly.
Okay. I wasn't even aware of it. No.
Um, yeah, this is what says on my list. So it's this one.
Wow, that's interesting.
So we don't have anything.
We don't. So what we'll do, I'll talk about it.
Oh,
Okay. Yeah.
And
Yeah.
one other thing, will you post your slides on Amazon?
They're already there.
Oh,
Yeah, including this one. Yeah.
So for the presentation, will we choose from like any paper at all, or will there be?
I will present this.
Oh, you'll give
Yeah,
us.
yeah. Totally.
And has
And
the-
I will also assign the names.
Oh, okay, great. And has the course syllabus been posted on the Piazza?
I haven't. I had prepared. Yeah, I'll link.
Thank you.
Okay, let's start. So, couple of things that came up. Firstly, um, regarding tomorrow's office hours, as some of you may know, the ECE PhD prelims are taking place. So my slots, unfortunately, happen to be tomorrow afternoon, colliding with my office hours. So I'm looking at the prelim assignments I have been given. So I think I would shift my office hours to 4 to 5 p.m. Because I'm done by 3:30. So if you need to meet me or talk to me for any reason, come during that time. Second thing, which was I was totally unaware of, that apparently this time around there is a discussion section scheduled for this course also. But there is no TA, or at least no official TA. Leon is just voluntarily helping me out. But actually, in a way, it is good because Leon was asking, is there a discussion section time? Because there are things that we don't want to waste the lecture time in. So I think what we'll do is we'll announce in advance if we intend to make use of the discussion section, for example, to walk over some tool or platform details or stuff like that. Okay, so we'll keep it there, but we will sporadically use it, or I might use it for a makeup lecture or something like that. Okay, so so don't commit to anything else during that, but we will not hold. I think the department, the reason they assign it is because if the course enrollment is more than 40, then there is actually an official TA, in which case the TA needs a time, but we will use it in this manner. So on demand, we will use it. Yeah.
I'm not sure if I heard right, so you said office hours are tomorrow?
Office, yeah, normally I schedule office hours on Tuesdays and Fridays 2 to 3, but tomorrow 2:30 to 3 I have one of the prelim exams, so I will hold the office hours 4 to 5. Okay?
Time for a discussion though?
Huh?
There's a time for a discussion.
But there is no, like I just said, there is no discussion because there is no TA.
I
Right,
see.
yeah.
Oh, you just like show up and just casual.
No. So don't show up unless we tell you to show up. Okay, which may happen maybe even next. Like every time we'll hand out the homework, we'll basically schedule a discussion section to go over that, and also to walk you through things. So we'll give you a few days advance notice. Tomorrow, if 4 to 5 is the discussion section time, then think of it as it's my office hours. Come to my office. Okay. Okay. So what I want to next go through is kind of walk through an example platform what under the hood things look like. And in this particular case, I decided to pick that Hexaware platform that I showed, of which I have several units, so it's a good candidate for certain projects also. So a typical platform, I mean, from a kind of a mixed hardware software perspective, there would be an MCU. On the MCU, you would have kind of obviously the low-level CPU and stuff like that, but and a whole bunch of interfaces so that you can talk to other things on the board. Usually these things run an operating system, oftentimes a real-time operating system, often called as RTOS, and then other features for sort of communication and security and storage and all, and finally, of course, kind of the application. In our case, the RTOS, or the OS that we are using, is the Mbed operating system, which I already mentioned. And so it comes with a whole bunch of APIs and all. One of the things I would urge you to do is just go to mbed.com, set up an account for yourself because you would need it, and just sort of look into the description of what that OS and all is. So just familiarize yourself. But at least create an account. Just start gaining some familiarity. Okay, so as I shown last time, there are a whole bunch of platforms that comply with Mbed. Hexaware is one of them. It's kind of relatively unique in the sense that it's meant to be wearable, whereas almost everything else is kind of just desktop type stuff. So this is what, if you open up, and it kind of looks like. Amazingly densely packed. There is a display. There are a whole bunch of along the edges there are capacitive sensors. The main CPU is called Kinetis MK64. Yeah, that's kind of the main CPU. And then on the reverse side, they have Bluetooth support for Bluetooth Low Energy. That's the same Bluetooth which your phones use to talk to a whole bunch of sort of common Bluetooth peripherals, which has its own MCU. So the way Bluetooth is a fairly complicated protocol under the hood. So usually Bluetooth radios come with their own little processor, and then through a serial link you talk to the main thing. So in this case, there is a separate 32-bit processor, again from the same manufacturer, which manages the Bluetooth part. There are a whole bunch of sensors, so you kind of see them around out here. I'll kind of describe them a little more. There is a USB connector, there is a connector using which you dock it to the programming board. So a whole bunch of stuff sort of sitting there. Okay? But the main MCU is a ARM Cortex M4, 120 megahertz, 1 mega flash, 256K of SRAM. As MCUs go, it's kind of reasonably rich. The BLE MCU is an ARM Cortex M0 plus. So it's a same family but much lower power and obviously slower, as you can see, and much less memory and all. But it has two radios attached to it, a BLE radio and a ZigBee radio, 80.15.4. This one is not programmable through Mbed. So Mbed only runs on the main processor. This one is programmed separately using its own dedicated thing, because all it is doing is it manages the Bluetooth part and basically exposes an API to this other processor. So this processor talks to it. One of my student, last time we used it, did figure out how to program it, because we kind of made some changes to the software out here, so we could do it, but it's a very different programming model. From a platform perspective, so what we have in something like this is, so there's a main MCU. This is that Bluetooth one with sort of the BLE SoC. It talks using a serial link. There are a whole bunch of sensors attached to it. So this is what is called an inertial measurement unit. So accelerometer and magnetometer and gyro. So accelerometer, for those who don't know, is acceleration, XYZ. If I have an accelerometer sitting on the table, what would be the readings? G. Yeah, 0, 0, and whatever, depending on the axis. One of them would be the G. Okay, so don't forget. Gravity is also there. Okay. Accelerometer, magnetometer. Magnetometer is sensing obviously Earth's magnetic field, but other things also affect it. Any source of any large ferromagnetic mass, speakers, kind of things, and a lot of typical lab setting, a lot of electrical equipment, and also AC current flow. Gyroscope. What does gyroscope sense? What about rotation? What angular what? X dot or x dot dot? Like, I mean, is it what is it measuring? So gyroscopes measure angular speed or angular velocity, okay, not acceleration. Barometer, temperature sensor, humidity sensor, ambient light sensor, and nicely an optical heart sensor. Okay, it's basically what is called as a PPG. It's kind of very similar to what like my Apple Watch has. Kind of the LEDs at the bottom. They shines light, looks at the return signal, and kind of makes some sense out of that. This BLE thing also attaches to 6 touch buttons. So they are a user interface that exists out there. There is a haptic feedback vibration motor, that little display, so OLED display, and some serial flash memory, and what else? This stuff is actually sitting on this little board. That's the programmable board, so the thing connects to it, and this has another processor on it, which is responsible for programming this guy. I mentioned last time that mbed defined a way for embedded systems to hook up to the desktop computers. So normally this processor or equivalent of this processor, which handles the programming in case of mbed compatible devices, sits on the device. In this particular case, because they were so volume constrained, they actually put it on a separate board. Okay, but point is that your desktop connects you via USB to this guy, and then this guy programs the main processor. Okay, in this case, it uses a switch. It can either program the main processor or it can program this BLE. Mbed, in this case, only runs on this part. Now, as I mentioned at the beginning of the class, since the class size is small and we have another device of which we have sufficient number of units, so we are going to use a different mbed device, but other than the specific mix of sensors and all, it kind of has a similar thing, but it's not variable. The main MCU in this case is actually pretty powerful. A whole bunch of capabilities, but it's very typical of what you would find in an MCU. So MCU, again, remember it has some processor, but memory, and then a whole bunch of peripherals. So in this particular case, there's a processor core, which is the Cortex-M4, and the nice thing about this particular processor is that it actually also has a signal processor in it. So it also has features optimized for DSP type functions, and it also has a floating point unit. Okay, many processors in this case do not provide floating point, but for a lot of stuff that we do now, particularly sort of machine learning type algorithms and all, they often need floating point. Sort of on-chip memory, clocks, a whole bunch of timers, analog interfaces. In this case, it has ADCs. It's a bit hard to read, but it has ADCs and DACs both, so it can take in and emit analog signals. It has support for security, so in particular, it has a cryptographic unit, so it can accelerate certain crypto functions. It has a random number generator. Random number generator is used by a lot of security protocols as part of the key mechanisms, and then a whole bunch of communication interfaces. I2C, UART, SPI, CAN, these are all examples of commonly available serial interfaces through which sensors and actuators kind of connect to it. When, for example, some of you might have played with things like Arduino and all, right? I mean, so they provide kind of particular ways of connecting shields and things like that to the main board, but the various pins usually correspond to the analog IOs and these kind of serial devices there to connect. So, and then finally GPIOs, which are basically uncommitted pins, which you can twiddle 0, 1, or where you can read the signal coming in. So nothing very special about this MCU. It's very typical in the sense, it's just that it's probably representing kind of a more of a higher end kind of thing, like you usually would not find crypto units and all on most MCUs. So it's kind of a higher end thing. And it comes from a family where I kind of just show where it resides. So in this particular family, as you can see, it's kind of representing, yeah, it is memory-wise the highest end, it has the most pins. So they kind of picked a more resource-rich MCU for the. Okay, that's the data sheet. Main thing that I would like to highlight is that when it comes to, when we hand out the first programming, first homework, there'll be a programming element to it. And one thing I want you to get comfortable with is that this is not, with embedded systems, you can't get away with, a lot of times, you cannot get away with simply thinking of it, okay, I'm going to just write code and whatever speed it runs and all. It makes a big difference to understand the underlying platform. When I'm writing on my Mac, I don't care about what processor it has and what peripheral units, because essentially the operating system provides me good support for these. But with embedded systems, you are much closer to the hardware. So the type of programming that you have to do, you'll be a lot more effective if you spend some time understanding and exploiting the capabilities of your processor. So let's even trivial things like at what time did the pin go from 0 to 1? Okay, I mean, if you were to attempt to do it purely in software by, for example, just repeatedly reading the pin until you see a 0 to 1 transition, not going to be very efficient, very accurate. So you have to exploit hardware features, in this case, those timers that exist, to be able to do it. So becoming familiar with the specific capabilities of the processor does become important. So just something to keep in mind as you kind of proceed in that. Okay, so that's what an MCU looks like. The next thing I want to talk about is, because for a lot of the tinier embedded systems, power and energy considerations are extremely important. And I want to talk a little bit about what's involved in this thing, and what kind of hardware support, and how can you approach this problem. So to be able to do that, it kind of I want to start out with what happens in what are the different ways power gets managed in computer systems in general. Okay, and what I'm talking about, while it is from the perspective of a processor, but the same thing applies to other parts of a system also, to the radio, to the other peripherals as well. So one way power is managed is to provide for a given hardware multiple operating modes, which have different trade-offs between the power they consume and the functionality they provide. So in a very coarse sense, in a very simple case, it might simply be no function, 0 power, and all the functions, full power consumption. But most of these things you would see provide a lot more. So you might see that for different parts of my chip, CPU core, the memory, the peripheral, they could be independently shut down, and then I may provide the user with modes like idle, where things are powered up but not doing anything. Stop the clock. So stopping the clock is a very effective way of preventing power from being consumed, because the power is only consumed when something is done. So if I stop the clock, nothing is happening. So at least the component of power which relates to activity goes to 0. There's still power because you have electricity being supplied, so there's still so-called leakage power taking place. And then in the extreme case, I can cut off the power supply and take the power down to 0. The challenge out here is that the more you shut down, the harder it is for you to preserve the state. That is what you need to remember, and also costlier it is to come out of that. So for example, let's say I do power off. Well, immediately it means the content of register, the content of SRAM, they're all lost. So if whenever I come back, before I go to sleep, I have to save them, and when I power back up, I have to reinitiate that. I may also need to reboot the operating system. So all those things kind of add to that. Also, when you power off, and then after that you restart, it's not as if I command the power supply and say turn on, and then immediately the voltage goes up. The voltage going up and all takes time also. It takes time for the clocks to come up. So, and that could be in milliseconds. So depending upon things, that going into a deeper state may not be very effective, and you might want to go into a shallower state. So usually processors provide or MCUs provide a whole bunch of power management states. Let me see if I had something out here. Yeah, this thing doesn't provide, but this particular processor, for example, does have many states, and there would be kind of some way of accessing it. Now, operating systems abstract this away. So for example, Mbed provides some APIs for you to put things into a shutdown mode. A very common way is go into this mode and wait for an interrupt. The idea is the system goes into a low power mode until now something happens. like a packet arrives or a user clicks a button or something like that. So this is one, reduce functionality to save power. And by the way, this is often called as dynamic power management. Next up is frequency scaling. And kind of the idea out here is that the performance of the CPU depends upon the frequency at which you are operating at, and the frequency at which you can operate a processor depends upon the voltage you are supplying to it. So by controlling the voltage in the clock, you can take the same processor and operate it at very different performance slash power modes. So in a simpler version of this, we only change the frequency. So we leave the voltage the same, we change the frequency, and so as we change the frequency, the speed will change accordingly and the power will change accordingly. So how do you think power will change the frequency? What's the relationship? Yeah, but with what? Is it proportional, like linear, quadratic, or linear? Yeah, or at least the so-called dynamic power part of is linear. There is also this other power which is always being consumed, and that remains static. So a good power model of digital systems is something proportional to f plus a constant term. So that proportional to f part should of course. What about the performance? What happens to performance as you scale frequency? Again, to the first order, linear, right? I mean, so what happens to energy for a given operation? So I want to do some operation. It would take n clock cycles. So if I scale the frequency, what will happen to the energy used for that application? Energy needed for that operation? It stays the same, right? So I'm lowering the power, but since the time goes linearly, so the energy remains the same, right? So now there are second order effects out here, because when you change the frequency of the processor, the rest of the system is still operating at the same speed, right? So the thing is the following, your bottlenecks may reside somewhere else. So if you increase the frequency from 10 megahertz to 100 megahertz, it doesn't necessarily mean that your system will do 10x better, because some other interface may become the bottleneck, and therefore your speed gains begin to peter off. So there are second order effects that you have to be aware of when you're doing this. Okay, and as I mentioned, voltage also has a role out here. So what is the role of the voltage? Voltage dictates what's the maximum frequency you can operate at. Okay, because if you increase the voltage, and ignoring again second order effects about effect on reliability and all, when I increase the voltage, then I can operate the processor faster. So F max goes up. So you can really think of this as kind of a joint problem, right? I mean, as I operate the processor at a lower frequency, I can also, if my power supply is so designed, lower the voltage so that F max equals to whatever frequency I need. So that leads to the third technique, which is voltage and frequency scaling, where what we do need is some support so that the voltage regulators, which are providing the voltage, are software controllable. And the idea is that now we make use of the fact that for CMOS technology, the power consumption takes the form is proportional to capacitance, is proportional to activity taking place, is proportional to frequency, and is also proportional to voltage square. So formula is alpha CV square F. Alpha says how much activity on each clock tick is happening. C is the capacitance in the system, V is the voltage, and so V square and F. So what this leads to is the following. I can lower the voltage and lower the frequency. So if I need a lower speed, my best win is to lower both of them accordingly. Lower the frequency and then adjust the voltage so that I can sustain that frequency, but nothing excessive. So this is called DVFS, dynamic voltage frequency scaling, and this gives you energy gains also. So the idea is, remember, in this case, when we lowered the frequency, we really didn't have any energy gain. All that happened is I can afford to do things over a longer period of time, but the energy consumed was the same. So my battery life would, to the first order, remain the same. With this, if you again take a very simple model that frequency and voltage are proportional, the F max and voltage are proportional, then you can basically say that my power is proportional to frequency cube, and therefore as I lower the frequency, I have a huge gain on the power. So this approach results in improvement in energy for a given computation also, whereas this approach keeps the energy constant. So this is better, but obviously requires more of your system. So the other courses have covered this. Okay, so in this particular processor that we were talking about, there is a power management controller, and it provides kind of 3 primary modes: run, wait, and stop. There is a special instruction which, and something like this you'll find in a lot of places, wait for interrupt. So the idea is, at some stage, I have nothing to do in this thing. There's no event, no task remaining. So you'll execute this WFI, and then we are going to wait until some event happens. A packet arrives, a button is clicked, or whatever, something happens, and then we go into this. And this processor also provides the reduced frequency mode and stuff like that. So there are a whole bunch of features. Again, to exploit these, one needs to be, you need to kind of look at the underlying platform. There is just no substitute for it when it comes to optimizing for performance and power. You've got to be familiar with the underlying platform. You can even with general purpose programming, if you are into the business of high performance or highly optimized, you have to do these things. You have to be familiar with how much cache you have, stuff like that. So people spend a lot of time optimizing. In embedded systems, that becomes even more important. Okay, so yeah, this just shows some plots. So I want to build upon this theme that a very common misconception that happens is between energy and power. So again, I'm sure all of you know, but energy is the integral of power over, right? I mean, so power is saying how much is voltage time current at any given time, and energy is the integral of that between some T1 and T2. And one has to be aware of this distinction, because oftentimes sort of people mix up the two, and depends upon what the objective is, right? As we saw earlier, I can have a low power system, but that may not be low energy, right? Because I can reduce the frequency arbitrarily to make it lower power, but then I'm just increasing the execution time, and therefore my battery will last equally long, right? I mean, it's not lowering the energy. So just as an example out here, imagine 2 processors. They're kind of a bit old, but sufficient to convey the point across. This one is 32-bit, 1 watt, 1 gigahertz. This one is 8-bit, 50 milliwatt, 10 megahertz. Now looking at this, you say, this is lower power. If I'm on a lower power application, let me use this. But if your goal is to optimize the battery life, then it's unclear whether this choice on the right is the better choice. And it turns out, depending upon what you're doing, it's not, and oftentimes it's not. So in this case, what I've shown is for 3 different computations: FFT, CRC, which is the cyclic redundancy checksum, and an FIR filter. What you see out here are on the left hand side in each plot is for the 8-bit processor, the execution energy, and the right one within each plot is the execution energy for the 32-bit processor. And the scales are different. So here the scale goes to 1000, 1000, and here it goes to 100,000. But the key observation is in each one of these cases, the energy consumed by this function is a lot less. Actually, this is a log scale, so there's even more demanding than it seems. is a lot less with the 32-bit processor, even though the 32-bit processor was, going back out here, was 1 watt versus 50 milliwatts. So in terms of power, it was much more expensive, but in terms of computation energy, the roles are considerably reversed. So why do you think it's happening? What all factors come into play? Okay, so 8-bit, so firstly right there, you can say that when we say 8-bit 10 megahertz, perhaps it is really equivalent to a much slower 32-bit processor, right? Okay, so that's true. Okay, so that's one. What else? I mean, do you think an 8-bit processor is literally just a 32-bit processor, but just 1/4 the bit size? No, right? I mean, what are the other things higher end processors have which help them? Okay, more memory, bigger caches perhaps, right? More registers. So they have a whole bunch of architectural features which help them be more efficient, right? More high performing. So architecture variations come into play, right? I mean, so when we are presenting this thing, it's not as if this is 1 watt and 1 gigahertz just in terms of the scaling. There's a lot of other architectural benefits that you also go out here. So which is why there is kind of a whole bunch of the scaling is just not just simply in terms of frequency and bit width. There's a whole bunch of other things which are coming into play. So a choice which is good for low power may not be good for low energy. Now in this case, I've deliberately picked pretty intense examples. On the other hand, if the computation was pretty simple, where the difference between the 8-bit and 32-bit architecture were to be not so evident, then the story would be different. So for simple computation, the story would not be like this. Now, even that is just one aspect of the story. The other thing is that these systems often do what is called as duty cycling. They are doing something, then they become idle. So we would like to put them to sleep. And then when something needs to be done, we want to wake them up, right? So this kind of idle, go to sleep, wake up when something arrives. So there, remember I talked about earlier on that when we wake something up, we have to fetch back the state that we had lost, and also that comes into play. So you will likely have a more state in a 32-bit processor than a 8-bit processor. You'll likely have a more complicated operating system, just generally a more complicated system. So putting it to sleep and waking it up is going to be more complicated. So that shows in the numbers out here. So you see, for example, in this case, the 32-bit MCU is kind of hundreds of microseconds and like order of 100 microsecond, order of 100 microjoule in terms of cost to the things. Whereas and in terms of that was a suspend, and in terms of resuming, it turned out in this case, like older versions of like it runs Linux, so milliseconds of resume time and millijoules of thing. Okay, so and while it is asleep, it consumes milliwatts of power, which is more than what my 8-bit platform uses even in active mode. This guy, on the other hand, when it's suspended, it's basically near zero power consumption, and so very different characteristics. So if my application is of a type where I'm going to spend a lot of time in the sleep mode, then the 8-bit one is going to handedly win out. So even though I may be inefficient in doing the computation, but if I do that computation once in a blue moon, I again win out. So a lot of like imagine a system like your home security system. Most of the time they're doing nothing. If you ever have a burglary, that's when they trigger. So when that event is happening once in a blue moon, then who cares about this? I mean, if it's going to happen rarely, then my overall life cycle, that doesn't matter, and I really should design for this. So what this suggests is the nature of application is going to play a big role, that should you focus on active mode efficiency versus should you focus on what is happening when the system is asleep. And so what that brings to is an objective which is referred to as energy proportionality. That is, I would like to design a system which consumes proportionately more power as I demand more work from it. So, so that way I can kind of scale the system, okay, nicely. If I need nothing out of it, it should consume 0 power, and if I get max performance out of it, it should consume the maximum power, and sort of linearly go between them. And we see that because most of these systems have pretty dynamic workloads. And the example of a smartphone, the maker's kind of a clunky old phone, but the concept remains the same, that if you look at what the workload on the system is, most of the time it's doing nothing, and then when we touch it, burst of activity happens. When maybe one of those dynamic widgets do something, again some activity happens. So like the clock tick here, that's when some action is happening. User is swiping, so again some action is happening. So sort of when events happen, then there's computation, and otherwise the system isn't doing anything. So what you would like is a system which, while not much is happening, it consumes lower power, because as we realize that when I am asking the system less, then a simpler architecture and a simpler processor will suffice. On the other hand, when I need some heavy duty thing, then that's when more power should be consumed. So if, for example, when I get an image and I need to do some analysis on it, maybe that's when I pay the high power penalty, and the system may begin to consume, let's say, a watt, and then other times maybe it's just consuming microwatt. That's ideally what we would like to have, as opposed to this view as if the processor is just something constant. So what that leads to is this challenge that the reality of hardware is that if you design something for peak performance, higher peak performance, then generally it is going to be worse off for even when it is doing nothing, right? I mean, so it's kind of like if you buy a race car, then it's going to be extremely inefficient even for city driving. On the other hand, if you buy a commute car, might be supremely efficient for city driving, but its peak performance is lower. So same thing happens with processors. So there are processors which are designed for higher level of performance, and they would have some sort of performance power curve, but it would be geared towards a higher peak performance. And so this is an example, and of course within this curve I can move back and forth using that dynamic voltage frequency scaling I mentioned earlier. I change voltage and frequency to kind of move, but there's a limited amount I can move, right? I mean, so even though that, again, race car analogy, surely the race car will consume give better mileage in city driving than it would while actively racing, but its city mileage is going to be worse than optimized commute car. So the idea then is maybe I can put a second processor out there, but this processor is designed for the more ordinary workloads. So it has a different voltage frequency, power performance curve, and now together these give me a wider dynamic range. But to make this thing happen, I need to figure out where to run my workload, right? Should I run it on the big processor or run it on the more efficient processor? But this concept sort of, as you can see, kind of makes sense and indeed has been adopted. So ARM, for example, is something called big.little. So what happens in this architecture is processors are paired. There are two cores, one core which is optimized for lower workload, so it's this yellowish thing, and one which is optimized for higher performance, and then it's the job of some runtime mechanism to figure out which one to activate, how to activate, should you use both or not. And And then finally, you may even have even tinier processors, more loosely coupled. Perhaps this could be even of a different instruction set architecture. So like in this ARM.little, ARM's big.little, the two processors are the same instruction set. So I can run my program in either place without any change, except with different performance. But maybe I can have a separate processor which is not even the same ISA. So TI, for example, has processors where they take sort of this big.little, and then they also attach a totally separate processor of a different instruction set architecture. So the idea could be that this little processor, which is extremely efficient, normally this is the only one which is up, everything else is asleep, is waiting for things to happen in the world, and when things happen, maybe it examines them, sees is there something interesting, if so, it wakes up the main thing. Okay, so there are many different ways one could kind of create these systems, but there is this hierarchy that you create of computing, so that resources which are optimized for big workloads are triggered only when you know that we would truly benefit from it. And most of the time we otherwise work with the more efficient smaller processors. So if we are successful, then what you would see is something like this, that when the peak workload arrives, then we are going to switch to the bigger processor core, and then otherwise we are working with the more power efficient, simpler processor core. And this rapid switching has to be managed by some runtime mechanism. It could either be the operating system, or could even be some sort of a state machine sitting on the chip in hardware, which is just monitoring how busy the processors are, and then kind of just switches back and forth. So this is a form of multiprocessing, multiple cores, except it is heterogeneous multiple cores. So normally, like when like Intel says I have a processor has 4 cores, what they'll really have is 4 identical cores. So that's homogeneous multi-core. This is heterogeneous multi-core. And why stop at 2? You can have kind of more of them. So this concept of making something, making a chip with multiple cores, but kind of a diversity of cores tuned for different points in the power performance space, and then letting the software carry the burden of activating the right set at any given time. This raises a lot of other challenges also, like for example, where should my interrupts go? Normally the task is simple, interrupt comes, I send it to the processor. Now you have to send it to the processor which is currently active. So there are a lot of IO related issues and all that also come up out here. But again, I mean at this stage, this is now a few years old type concept. So it's pretty routinely done. So one of the early exponents of big.little was Samsung's Exynos chip, which they use in the phones which they sell outside US. But Qualcomm chips and Apple also uses it now. So this big.little is a pretty standard technique over the past 2-3 years now. And sometimes things don't work very well. So the previous generation of Qualcomm chips were well known to be energy hogs, because whatever power management feature they were using for switching these things wasn't working. So they had extreme inefficiencies in that process. So these are pretty complicated under the hood control that happens, but if you get it right, there are a lot of benefits to be had. So in this Samsung thing, again, what you would see out here is that there are 4 big processors out here, A15, and 4 smaller A7 processors, and then kind of one switches back and forth. And there are additional constraints, like it's within each pair, like you can have only one processor up. So like you have to make a choice of big or little. You can't have both up. So anyway, that's the concept. Okay, so A7 and A15, identical instruction set. So your program can run on either one of them, but different microarchitecture. By different microarchitecture, I refer to how much cache they may have, how do they do things like branch prediction, how many instructions do they execute simultaneously. There are all these capabilities that modern processors have to speed up things, but they come at a cost. So so you see, okay, A7 is an in-order processor, which means it executes instructions in the order they are in the program, and it has a pipeline of 8 to 10 stages. A15 is an out of order, so it does what is called a speculative execution. So it could go ahead with, even though a current instruction isn't finished, or it can do, it can try out when you hit a branch, it can go ahead and start executing the branch in anticipation that it is right. So all those kind of features that modern, and this pipeline is a lot deeper. Single queue for its 5 execution units, so the instruction set on a single queue. Here it has 8 execution units, and each one of them has more complicated queues. 2 instructions can be executed per clock cycle maximum. Here 3 instructions. So it is more processor optimized for higher performance, and therefore its power performance curve is kind of separate place. So that's the big dot little concept, and the operating system has to make sure that we kind of traverse this thing seamlessly by smarter scheduling and things like that. I'm going to stop out here. We're going to pick up this thread on Tuesday. But one takeaway from today is this power versus energy, and this kind of hierarchy that you seek to create to get a wider dynamic range.